In the introduction lecture, we had seen that a collision occurs when a key is mapped to an address that is already occupied. Now, since we cannot place this key at the address given by the hash function, we need to find an alternate place for the key. And for this, we can use one of these two collision resolution techniques: open addressing and separate chaining. First, we'll learn about open addressing. In this technique, we'll place the colliding key at some empty location inside the hash table itself. So when we find that a key is mapped to an already occupied address, we'll start searching for an empty location inside the table. We'll see three methods for finding an empty location inside the table: linear probing, quadratic probing, and double hashing. First, let's see this linear probing. In this technique, we'll place the colliding key at the next empty location in the table. So suppose we have a key K and it is mapped to some address A by the hash function. Now if this address A is empty, we can place the key there. But if it is already occupied, then we look at the next location of the table. So we look at address A plus 1. Now if this address A plus 1 is empty, we can place the key at this address. Otherwise, we look at address A plus 2. So we keep on trying successive locations till we find an empty location where the key can be placed. And in this process, if we reach the last position of the array, then we can resume our probe from the 0th position. Now suppose we have a hash table of size 11 and a key is mapped to address 7 by the hash function. Now if this location 7 is empty, there will be no collision and we'll place the key here. If location 7 is not empty, then we look at location 8. If location 8 is also not empty, we look at location 9. If 9 is also not empty, we look at location 10. If 10 is also not empty, then we'll look at location 0. And then we look at locations 1, 2 and so on. So we search for empty locations in this sequence. So basically we are linearly probing the array and we place the key when we reach an empty location. Now we'll take a hash table of size 11 and we'll insert some keys in it. We'll use this simple hash function, and whenever there is a collision, we'll use linear probing to resolve it. Now first we have to insert key 57. It is mapped to location 2 by the hash function. This location 2 is empty, so this key is inserted here. Next, we have to insert this key 40. It is mapped to location 7. Location 7 is empty, so we insert it here. Next, 69 is mapped to location 3. 3 is empty, so we insert it here. Next, this 54 is mapped to location 10. This location 10 is empty, so we'll insert this key here. Next, we have this key 29 and it is mapped to location 7. Now, location 7 is already occupied. So, we'll look at the next location. This next location is empty, so we can insert the key here. Next, this key 76 is mapped to location 10 and location 10 is already occupied. So, we look at the next location. This next location 0 is empty, so we can insert the key here. Next, this key 35 is mapped to location 2. This location 2 is already occupied, so we look at the next location. This next location is also occupied, so we look at the next location, location 4. Now this location is empty, so we can insert the key here. Next we have to insert this key 87. It is mapped to location 10. Location 10 is already occupied, so we look at the next location. This is also occupied, so now we look at location 1. It is empty, so we insert the key here. So this was the explanation of how insertion is done in the case of linear probing. Now let's see how to retrieve a record. For retrieving a record, first we'll get the hash address by applying hash function to the key. Now if the key is not found at the hash address, then we'll search linearly after the hash address. The search is successful if we find the key, and the search is unsuccessful if we reach an empty location or we reach the position where we had started. Now for example, in this table, if we want to search for key 35, then first we apply the hash function. The hash address comes out to be 2. Now key 35 is not present at hash address 2. So now we'll sequentially search for 35 till we reach an empty location or we come back to address 2. So we look at address 3, 35 is not present here. Now we look at address 4, 35 is present here. So the search is successful. Now suppose we have to search for key 65. We get the hash address 10. Now 65 is not present at hash address 10. So we start searching sequentially. Now 65 is not present here. It is not present here, not present here, not present here, not present here. Now we have reached an empty location. It means that the search is unsuccessful. This key 65 is not present in the table. We can write the formula for linear probing like this. This h is the hash function. This t size is the size of the table. And the value of I varies from 0 to table size minus 1. Here we have done this mod table size so that the resulting address does not cross the array boundary. So while searching for an empty location, the sequence of probes would be this. First the value of I is 0, then 1, then 2, 3 and so on. The sequence of locations that we examine is called probe sequence. We have seen earlier that if we have a hash table of size 11 and a key is mapped to location 7 by the hash function, then this is the sequence of probes. Let's verify this by using the formula. This is how we get the sequence by using this formula. Hash value is 7, table size is 11, so I goes from 0 to 10. And each time we are doing mod table size. So we get the same sequence by using this formula. Now let's look at a problem that we face in linear probing. When almost half of the table is occupied, there is a tendency of cluster formation. Now these clusters are nothing but groups of records placed next to each other. For example, in this table, we have this cluster formed by locations 10, 0, 1, 2, 3 and 4. Now because of these clusters, the search time of a key increases. Now if a key is hashed to any of these locations within this cluster, then it will be stored here at index 5 and this cluster will increase in size by 1. This problem is called primary clustering, and because of this, the number of probes required to insert or retrieve a key increases and it reduces the performance. Now once a cluster is formed, it is more likely to grow by insertion of more colliding keys. So the bigger the cluster gets, the faster it grows. For example, if we have a cluster of 10 locations, then any key mapped to these 10 locations will be added at the end of the cluster. If we have a bigger cluster of suppose 50 locations, then chances of this cluster getting bigger are more because now any key mapped to any of these 50 locations of this cluster will be added to the cluster. So bigger the cluster gets, the faster it grows. There is also a possibility that two clusters join and form a bigger cluster. For example, in this case, suppose after some time all these locations are occupied. Then these two clusters will join and we'll have a bigger cluster. To prevent this primary clustering problem, we can use quadratic probing technique, which we'll discuss in the next lecture.